All right, today we're going to review FEA, or finite element analysis. And if you've gotten this far, I hope you can make a shape like this. If you can't, please go back and watch the other tutorials. We're just going to start with this. And to start your FEA, you're going to want to go to Simulation, under the Simulation tab. You're going to click New Study. And in this case, we want a static. So there's other ones to choose from. For example, if we just keep open all these up, um, these static, and essentially a static is everything is still. Like you're just taking something at an instant point in time. This frequency, it helps you find these things like the natural frequency of the object. So if this thing, basically it would cause harmful interference, or something could cause harmful interference to it. So if you've ever seen essentially uh, maybe a video where glass and you play a sound at the natural frequency at a high enough amplitude, it will break. That's kind of a similar concept to this. It's not necessarily going to break. Technically, it could. It'd have to be a really large amplitude, and but it's just mainly to help you understand at kind of which frequencies it starts acting different, or maybe starts vibrating or something like that. Topology study, that helps you remove material. So it looks at all the loads and it's like, oh, you can remove this bit of material. We aren't going to do that today, but similarly, a design study, say you have parameters, you don't know which one's best. So for example, and we definitely could do this one. We're just going to have like a foot stepping on this. So it's going to be like 120 pounds or 150 pounds pressing down. Um, and so a design study would look at each of the different parameters you set it to. So, for example, these two little legs, and it, uh, according to your specifications, it would go between a range of maybe 1 inch and 5 inches. So maybe the wider they are, the more likely it is to support, or the easier it is for it to support your foot. And you can do more complex calculations and designs whenever you have it trying to optimize for least amount of weight and most factor of safety. So I use design study the most. Um, but moving on, there's other simulations like thermal, buckling, fatigue, um, and more. Fatigue is something you might use for cycling components. So, for example, like a drivetrain, would it withstand 10 to the power of 7 cycles or whatnot? Um, it just helps you understand like how the material and the piece you make reacts to loading and unloading and cycling and stuff. Drop test and pressure vessel design, I haven't necessarily used that much, or at all. Pressure vessel design, I'm sure it's just pressure going outwards, and the drop test being just if you drop it, what happens. But right now we're just going to use static. We're going to hit the check mark, and now we can start. And so you just get these options up here. So apply material, I already have a material, 1060 alloy. I just picked a material, honestly. Um, but next up is these fixtures. There's always a fixture advisor. It opens up a thing to the right. So basically, if you know what forces your object is going to have on it and what kind of loads, you should be good. But if you don't know how the stuff interacts, you should probably add in the pieces. In this case, um, there's a thing called fixtures, and there's different stuff like fixed geometry, hinges, elastic like springs, and advanced stuff. Usually we just use fixed geometry. And see, it kind of gives a little example, and this is usually pretty helpful. Um, but you see, we actually want, since it's a kind of like a stool on the ground, we want the bottom two faces just to stick exactly where they are. So no matter kind of what you do to this piece, these faces aren't moving anywhere. Obviously, the rest of this material here is free to move, um, but these are not. So we just hit the check mark on that. And now this stool is fixed in place, right? We can't move it. Um, that was an accident, but can't move it from the bottom. External loads, this is where you get a lot of different options. So there's also an advisor for this one. Um, and so wind load, payload weight, user applied load. So also static studies assume that the load directions do not change. Um, so essentially that means if I press down, if I have a force coming down on this, say it's opposite of this arrow, it's going to continue going down. Um, and that's a case kind of with a foot. But maybe there's some things where it's pressing down and the surface kind of bends and it turns that force, like the force direction changes. You'd have to use an interaction for that. But in this case, we don't really need that. So I'm going to add a force. We're just going to add a force. And notice it selects the entire face. We don't really want that because our foot, while it could be over this entire face, um, unless you're Gigantor and you have a foot that's like 14 inches long, that's not going to happen. But just really quick, we can actually split the surface and we can create a sketch. Um, if we select this top surface here, just like that, we can draw a little rectangle. And you'll notice you can't dimension it, but if we just do that, we can create the split. And now it's just on that face, right? So if I, just on that face. So arrows are pointing down. So all the force that we're putting into it is just going over this rectangle. And just really quick, let's just say it's a 150-pound individual and they're standing on one foot and all their mass is distributed over the center of this. Obviously you can do this thing called, hold on, a remote load slash mass, which means theoretically someone's center of mass could be up here and this area over here. So like centered, say this is their left foot, could be centered and they're standing on their left foot with their right foot not touching anything. And it would do all the math of how much force and all that other great stuff on the surface with the center of mass over a little bit because that changes things. Um, so we have it says 100 or excuse me, just edit this definition. 33 pound-feet. No, we want 150. Just go like that. That's 150 pounds over this area. And it, like we said earlier, it wasn't centered or anything. So what we need to do is go back to model, and the option is split line. You can actually create these split lines if you just go up in the commands and you go split. And you can create sketches and split lines so you don't have to do that in the simulation tab. But what we can do is we can actually edit this sketch. So let's say homeboy's foot is 4.5 inches wide and it is a size 11. Just like that. But we can still kind of move it around if you notice. So what I'm actually going to do is I'm going to create a point right in the middle, just like that. I bet you can move that around. Yep, you sure can. All right, well, we're just going to do it a little bit of a more direct way. Smart dimension. Grab something like that. Maybe it's 1.5. And grab something like that. And maybe it's 1. Might be too much. Actually, let's do it off to the side a little bit, see what that does with the calculations. So now we have a fully defined sketch there. We can go back to static 1. You'll notice how everything has shifted over, everything's updated, which is helpful. But also all these planes are not hidden. So I'm just going to hide those real quick. Just makes everything easier. And so now you notice we have this. It's supported on the bottom, and there's a force coming down on the top. We'd expect this thing to end up bowing down, displacement-wise. Stress and strain, there's going to be a lot of stuff, I bet, there, and also in this middle here. So actually, just over this entire part. But really quick, I'd like to go over connections. Um, while in connections, say I made this top piece and this foot holder support, a second piece, and there was holes in here, you could use this bolt or whatever, and you can select the circular edge of the bolt hole and the bolt nut hole. So there's a whole bunch of just different options. Like, say I put pins in there, right? You'd select the faces that of the pin. So you can only do one at a time, and like there's different connection types. Um, there's different like this is stiffness. There's rotational stiffness. There's also mass of the entire thing, um, which also affects stuff. So if you have like a really light plastic piece, and say you're doing something with a metal pin, it might be affecting that plastic piece as well. So there's definitely a lot of just different options. And say you even have springs. I've never used a spring. I've never had to. Um, but essentially, it is possible to do. There's different normal stiffness, tangential stiffness, rotational stiffness. All these essentially numerical values, they'd be part of the values for a spring. So the stiffness, that would be the value there. And there's just different values for all that different stuff. That all goes into the equation. Next up is, I've never used Shell Manager, but or this diagnostic, but next up is creating a mesh. There's different densities you can do. So if I do a course, I'll just do it real quick. This course mesh. See how wide the different little sections are? If I change that, create mesh, I want it to be fine, they're a lot finer. So this is where FEA, it's a good time to talk about FEA. So these little meshes, these little triangles, that's where it does all the math over. Um, Essentially, when you have a regular piece, the forces act over an infinitely small area, and that all gets added up essentially. Here it breaks it into sections so where the computer can actually do the math, and you get a pretty decent estimate of what's actually going to happen. Obviously, it's not perfectly accurate because these little mesh sections, these polygons, aren't infinitely small, but you can, there are limitations um, on this. So like if you go into advanced and Jacobian points, you might learn about Jacobians in Calc 3. Basically, it changes one section of, or one coordinate system into another. And there's also just different mesh parameters too. You can set different like max element size, minimum element size. So there's a lot of just different stuff you can do. So we're going to do fine for now because my computer can handle it. Um, so if we just do this, if you zoom in actually, you notice this rectangle we made? The bounding box is all straight lines. So basically the computer knows what area the force is going to be applied over, and same with this bottom here. After that, we can run the study. And just like that, it is done. So if I just go back to stress, here's what the stress is. Um, and notice how right here, there is a lot of stress. Oh, there's a lot of stress. Here there isn't as much. So the blue areas have the least amount of stress. And you'll notice that the yield strength is 2.7 blah times 10 to the 7. You do not want um, the stress of this somewhere on this scale to be higher than your yield strength. That just causes issues. So obviously these blue parts, it's a power of 10 to the 3 difference, at least. So I'm actually going to go to displacement, and you'll see this. So you notice how, if you remember, the box was more to this right side, and that definitely shows with the displacement. So it says that the maximum displacement for your model is 3.95 times 10 to the negative 2 millimeters. So that is 0.0 4 milliliters. So that is quite small, honestly. So that means whenever you step on this with that force, that's how much it's going to displace. Um, and here's another strain. Stress and strain, they're kind of intertwined. They're kind of not. They have two different meanings. Um, but there's those values for that. And if you hit right click, you can actually do factor of safety plot. There's different um, plots you can do and compare results. But if I do factor of safety plot, say check, you'll notice that um, essentially this red part, it says the minimum factor of safety is 5.3. And for most automobiles that are coming off of the line that like officially have to meet standards, it's going to be a 5 that you have to meet. But obviously, if you go back, apparently this spot here is 1,709 as a factor of safety, which might be a completely outrageous number. It definitely is. So usually you can go to settings, not settings. You can go back to edit it, edit the definition, and set the upper factor of safety to say 6. So once you do that, you can just see different differences. So you can see right here, it highlights the colors differently and better. So as you can see here, that is where that factor of safety of 5.336, that's where it's affecting it the most, and probably same symmetrical over there. So that's what that does. Most of the time, you'll look at factor of safety, you look at the stress, make sure the numbers make sense, and that's one of the main things. Like, is this a result we would expect? And I would say it is, yes, because we're stepping on it on the right side of it, more on the right side. So that's why it's heavier displaced over here. We have fixed these, and we would expect in real life it to behave like this. So that is that. Obviously, there are so many different um, external loads you can put on here. So for example, at temperature. So there's a lot of stuff you can do with temperature. So if I just select that face, um, temperature, say I want it in Fahrenheit, just like 55 degrees Fahrenheit, right? Just hit check. So that side's 55, and we're going to do another temperature here. We're going to do on this side, Fahrenheit. Maybe it's 200 degrees. And I'm not sure what this is going to do, but we can just run the study again. Remember our 3.95? You'll notice stuff changes, as you can see. Um, and if we look back at our stress, it looks like this cold side looks like it's fine. But whenever this side is applied 200 degrees Fahrenheit, it starts kind of warping a little bit and more displacement. You'll notice our displacement has changed as well. And so with that heat, it looks like it's also changing some numbers. And that's probably something we would expect. Look at the factor of safety again. Right there is apparently not safe. And that's probably because it's a directly applied temperature. It might not have very good heat transfer coefficients. But essentially, that is how FEA works. Divides it into little sections, does the math, and puts out some results. So there'll probably be another video eventually on different studies where we take something like this and we optimizing it, use it design study. But I hope you got something from this video, and I'll see you in the next one.